Okay, so let's continue. For the next few lectures, we're going to look at trusses, okay? Specifically truss structures. Okay, before we move further, okay, let me recall what we did last time. Okay? So we developed the truss element stiffness matrix. Okay. And so if you recall our developments, is we're looking at an element like this, okay, nodes I and J, okay, and at each one of the nodes, okay, we have a force, okay, Fi, right, and then the corresponding displacement, delta I, okay, and likewise at J, Fj, and the corresponding displacement delta J, right? Of course, the element is embedded, right, in the coordinate system where axis points to the right, and so positive quantities, namely displacements of forces, are to the right, and negative are to the left. Okay, and so we derived the following relationship. Okay? Is if you want to compute Fi, Fj, okay, like this, from the end node displacements, delta I, delta J, okay, the solution of the underlying differential equation gave us the following relationship between forces and displacements. EA over L minus EA over L minus EA over L, EA over L, okay? And so, because you're looking at the relationship between displacements and forces, and so far you've seen, elements like springs and what relates the displacements to forces, right, or what the spring stiffness. And what you've seen so far, that spring stiffness was always a scalar, right? You'd be a scalar displacement in the direction of a spring axis, and that would be related to the force by a spring stiffness coefficient. Okay? So for this system, right, we have two forces. So this is a 2x1 vector, right? We have two displacements. This is a 2x1 vector. Okay? So the object that emerges is a 2x2 matrix, okay? And this becomes the truss element stiffness. This is the stiffness matrix. Okay? So now, supposedly, okay, let me assume the following displacement state. What if delta I equals to delta J, okay, equals to some delta? Okay. So what this means, nodes I and J move in the same direction by the same amount. Okay. So what this means, U bar is translating. Okay. And so from your understanding of the strength of materials and mechanics, what do you think is going to happen? Okay. Well, let's see. So if I compute Fi and Fj, okay, for this situation, EA over L minus EA over L minus EA over L, EA over L, I plug in my displacement state, delta delta, okay, and what I see is, right, this EA over L will multiply this delta minus EA over L, multiply this delta, we'll add it together, you get a 0. Okay, so Fi is 0. And the same things happens for Fj. Minus EA over L will multiply this delta, okay, plus EA over L multiplying this delta, I get another 0. Okay. So what we're looking at here is the translation mode. So physically, right, if something translates, it shouldn't build forces. And this is exactly what's happening here. Okay? So this is known as the example of what's called a rigid body motion. Motion, or RBM. Okay, we'll see more and more of those in the class, but as you know from mechanics, right, if a body undergoes a rigid body translation, then that includes displacements and rotations, right? In this case, this is just a one-dimensional system, right? Can only translate left or right. There's no rotation yet. That body should not build forces or stresses, okay? And this is exactly what's happening here. Right? Okay, so then, if translations don't work, okay, then the only way you're going to build forces, right, is through what? Relative displacement between the nodes. Okay, so relative nodal displacement will produce forces. Okay, so mathematically speaking, okay, the quantity that we need to look at is this: delta J minus delta I. Okay. And so let me label this relative displacement, right, to sort of foreshadow what's coming by delta over bar prime. Okay. That notation will surface later in the class, right? But think of this as sort of basic element displacement. Okay, meaning it's a displacement with all of the rigid body translations sort of filtered out. Okay. And so now, if I apply delta I, delta J, okay, that looks like this: delta prime 0. Okay, it means I will apply relative displacement to the left node, okay, and then I keep them. Doesn't matter which node I center. In that case, right, F I, right, and Fj become EA over L minus EA over L minus EA over L EA over L times delta over bar prime 0. Okay, so let's do this calculation. EA over L multiplies delta prime minus EA over L multiplies 0. I get EA over L times delta over bar prime. Okay, and in this in the second slot, it's minus EA over L times delta prime 0 over L delta over bar prime. Okay. Right. So pictorially then, okay, what do I get? All right. So if I define F over bar prime to be EA over L, okay, I'll put that in brackets, times delta over bar prime, right? So if this element subjected to a relative displacement of delta over bar prime, right, it will develop forces F prime over bar to the left, and on this node, right, minus F prime over bar. Okay? And the relationship is going to be like this. Okay? Right? So you see, if delta over bar prime is greater than 0, okay, it means that the elements in tension and then clearly F over bar prime is greater than 0. Okay. If delta over bar prime less than 0, it implies F prime is less than 0, okay, and we get element is in compression. And so starting from this general, right, this 2 by 2 relationship here, right, what we boil down to is the element is to something that's referred to as the element basic system. Okay, so in that element basic system, and again, I'll remind you, talking about trusses, right, and we'll talk about beam bending, the basic system will look a little bit more complicated, right? But at this stage, we define F over bar prime. We'll call this the basic element force. Okay, and it's constant throughout the element, equals to delta over bar prime, right? This guy we call basic element displacement. Okay. And the two are related through K over bar prime. Okay, this guy is exactly EA over L, and we call it basic element stiffness. Okay. So for a truss element, we have this very simple relationship. This is a 1 by 1 vector, this is a 1 by 1 vector, and this is a 1 by 1 matrix. All right. So now that we've introduced the basic system, right, let's start developing methodology in order to handle the full structure. This takes us to page 2.1 of the notes. Yep. Right, and the idea here is, again, supposedly you want to handle a situation where you're analyzing a bridge, okay? So let's say this is a bridge deck, right? You're going to have a couple of pylons that are supporting it, right? And so you'll have a connection here, you'll have a connection there, this deck extends, and then right, you're going to support it also by cables like this, okay? Something to that effect, okay? And so of course this guy goes into there could be water here, right? And then this guy goes into some foundation. Okay? And so of course you're interested in how the structure responds to traffic vehicles, right? You can have a car riding through this thing, right? You can have a wave action here and here, right? And then you can have an earthquake coming, okay? And so then your foundations are going to move left and right and possibly up and down. And so all these combined loading types are of interest, right? So everything we looked at so far involved an element that's sort of oriented along the horizontal x-axis. Then how do we handle situations like this, for example, right? Where you have elements that are situated in space in the sort of the arbitrary fashion. Okay, and so for this, right, we need to develop, okay, for truss or bar element, truss or bar, same thing, okay. And we need to develop transformations. Of end displacement and forces. Okay, good. All right. So the machinery that's involved here, right, is as follows. So supposedly you have a fixed coordinate system, and I will use capital X, capital Y here. Okay. So coordinates X and Y are a part of a global reference system. Okay, so independent how the structures are oriented in space, how they're connected, okay, that coordinate system stays in place. Okay, and that's what you've been used to. Okay? And then I'm going to take my element, I'm going to orient it in space in an arbitrary fashion. Okay. So by the way, again, we're going to do everything in 2 dimensions for now. Okay, I think this is sufficient. There's some additional difficulties that are involved in 3D. We'll see if we can get to those, but I doubt it. Okay. And so now that element again has arbitrary end nodes, I and j. Okay. And what makes sense to do, right, is sort of pretend that my little x-axis, right, continues to line up with the element axial direction. So little x is going to go like this now. Okay, you see the difference? And then little y is going to go perpendicular. Okay. And starting at node I. Okay. So this guy is before, right? Nothing new, has the length, L, has properties EA, okay? But now is oriented at angle phi, okay, to the big x-axis. So the coordinates little x, little y now, okay, will define an element local coordinate system. Okay, and so as you'll see, right, this is a pretty powerful construction. You can do many things with it. Okay, so in fact, even in finite elements, you have sort of a global reference and local coordinate systems, and this is how the FEM technology is developed. So again, you're touching on realistic things here. Okay? And so by looking at the picture, we can conclude a couple of things, right? We can compute the change in the x-coordinate, right, by taking the coordinate x of node j, okay, and subtracting the coordinate x node I, right? So this xi and j is the x coordinate of node I or j, okay? So if you look at the picture here, right, this distance here will be delta x, okay? So likewise, I can compute delta y, okay, by taking y at j and subtracting y at I. Right? And so now, again, thinking ahead, right, if you have an element situated somewhere in space, you will need to sort of figure out which one is node I, which one is node j, right? And this sort of a bookkeeping aspect of this is up to you. Okay? And so of course y are the y ij are the y coordinates of node I or j, okay, as before. And if you look at the plot here, right, this distance becomes delta y. Okay. So it's easy to see that if you take delta x squared, you add delta y squared, and then you take a square root, you get the length of the bar. Okay. And so now, rather than giving you the length, typically the problem statement is going to be the bar is going to be somewhere in space. These are the end node coordinates, and then you compute the length from there. Okay? And there you can construct a relationship, right? From geometry, if you want to compute cosine phi, you get delta x over L. Okay? And if you want to compute sine of phi, you get delta y over L. Okay? And so again, these are the relationships that you're going to be utilizing over and over again in the course. Okay. All right. So now, with these considerations, okay, let's take our bar situated somewhere in space. Okay, this would be node I, this would be node J. Okay, leftmost, rightmost. And then we see, okay, look, the node I, okay, can displace in the x direction, global x, right? And then I can denote that displacement to be delta 1. It can also displace in the y direction, and I can denote this displacement as delta 2. Okay. Likewise, node I can build forces in the x direction. I'm going to call it F1. And forces in the y direction that I'm going to call F2. So this element here is embedded into this global coordinate system, xy, right? And so, of course, the delta 1 and delta 2 are lined up with the x and y coordinate system, as you would expect, okay? Right. However, node J can also move, right? And it can move on its own independent of node I, okay? Which means that in principle I can have a displacement in the x direction that I'll call delta 3, okay? And a displacement in the y direction that I would call delta 4. And then the associated forces become F3 and F4 like this. Okay. Right. These can be packaged into vectors. Delta, okay, delta 1, delta 2, delta 3, and delta 4, okay, displacement vector, and force vector, F equals to F1, F2, F3, and F4, okay? So these are called global degrees of freedom, okay, or DOFs, at element nodes. Okay. Right. So these are displacements and forces, okay, quantities, defined at element end nodes, okay, I and j, referred to the global coordinate system. Okay, so that's why they refer to as the global degrees of freedom. Right. Now, I can draw the same picture from the standpoint of a local coordinate system. Right. So this is my node I. This is my node J. Okay. This guy forms angle phi with respect to the big x-axis. Okay, we know that. Now I have little x-axis that's lined up with the axis of the bar and little y-axis that goes perpendicular to the bar. Okay. All right. And then, just like in the global coordinate system, right, I can say, look, the node I can displace in the little x direction by an amount that I call delta 1 prime. Okay? Note the difference between delta 1. So here's the prime notation. Everything that's referred to a local coordinate system will be denoted by primes. Okay? And then there could be the corresponding force, okay, F1 prime at node I. Okay? Likewise, I can have a displacement along the little y-axis. I'm going to call it delta prime 2, and the corresponding force F prime 2. Just like in the global case, node J can displace independently, right, with a displacement delta prime 3 and the corresponding force F prime 3, right, and local vertical displacement delta prime 4 and the corresponding force F prime 4. Okay. So all of those can also be packaged into the vectors delta underscore, right? Underscore means vector, okay? But now it's no longer delta, it's delta prime. Okay, there's a difference. And this is delta prime 1, delta prime 2, delta prime 3, and delta prime 4. Okay, and likewise, f prime underscore becomes f prime 1, f prime 2, f prime 3, and f prime 4, like this. Okay, and so these become element, not global, but local degrees of freedom, DOFs. Okay. Again, local here refers to the fact that displacements and forces are referred to the local coordinate system. Okay. So delta prime 3 would be the amount that node J displaces by in the little x direction. Good. And so, right, clearly, let's say when you look at this picture here, right, let's say you're interested in the displacements of each individual node. I'd say this one. Oops, oh, that was a bad move. So you want to know how much this guy moves in the x direction. Call it delta x, right? And how much this guy moves in the y direction, delta y. Right? And so when you sort of report results and compute the entire structure, you have no choice but to refer everything to a fixed global coordinate system. Okay? Right? However, when you do the calculations at the element level, right, that's not the coordinate system you want to use, because that's not where your differential equation lives, right? Your differential equation lives in the axial direction. So for that one, you need a local coordinate system. Okay? And so as you've guessed it by now, somehow you need to, do some operations at the local level, okay? And then you need to bring things to the structure level. At the local level, things will live in a local coordinate system. At the structure level, things will live at a global coordinate system. So then you need to relate them. Okay? And so let's relate the coordinate system. And let's start with displacement vectors. So relation between delta prime and delta. Okay, well, so let's zoom on the node I. Okay, right, this is our element. And you can have a displacement like this, right? Delta 1 and delta 2. Okay, so this is angle phi. Right? And then you can also have a displacement delta 1 prime, right, and delta 2 prime. Okay. So, right, if you're interested in delta prime 1, okay, then you could see, right, there'll be a contribution from delta 1, right, and then there'll be contributions from delta 2, right? And the contribution from delta 1 can be expressed as delta 1 times cosine phi, right? And then the contribution from delta 2 from geometry, right, will be sine phi, like this. Okay? You can likewise write down an expression for delta prime 2. Okay? And then delta prime 2, there'll be a contribution from delta 2, right? This is phi angle, right? And then there'll be a contribution also from delta 1, like this, in fact, in the negative direction. So you can see that this becomes delta 1 minus sine phi plus delta 2 times cosine phi. So another way to write this would be delta prime 1, delta prime 2, okay, equals to cosine phi, sine phi, minus sine phi, cosine phi, okay? Delta 1 and delta 2, okay? So what does this look like, right? It looks like an operation that takes delta 1, delta 2 and rotates it into delta prime 1 and delta prime 2. Right? So I'm sure you've, in part of engine 40, perhaps you've seen these type of rotation matrices, right? Parts of dynamics. And so this is exactly, I'm going to call this guy R, okay? This is a 2 by 2 matrix. And this becomes a rotation matrix. Okay. That rotates at node I, displacements that are pointing that are referred to the global coordinate system, into the displacements that are referred to the local, okay? The rotation matrix. Right. So now, I can go ahead and repeat this for node J. Okay. I have my delta 3, delta 4, right? And I have my delta prime 3 and delta prime 4, right? And guess what? These use the same angle, okay? And so as a result, right, without going into too much detail, you can see right away that delta prime 3 and delta prime 4 are related to delta 3 and delta 4 through the exact same transformation. Okay? Because the bar is straight. So this becomes cosine phi, sine phi, minus sine phi, cosine phi, like this. Okay? Good. All right. And so, see, 1 and 2 are related independently, 3 and 4 are related independently. So now I can package the whole relationship into one. Delta prime 1, delta prime 2, delta prime 3, and delta prime 4 equal to. Okay? You get a matrix like this. This is 4 by 1. Okay? This is 4 by 1. And this is delta 1, delta 2, delta 3, and delta 4. Okay? And here I get cosine phi, sine phi, 0, 0, minus sine phi, cosine phi, 0, 0, 0, 0, 0, 0, right? And the 2 by 2 block repeats. Cosine phi, sine phi, minus sine phi, and cosine phi. Right? So two independent transformations, right, for node I and for node J, but everything packaged into one 4 by 4 matrix. Okay? So this now becomes what I call a big, rotation matrix, the rotation matrix. And the nodes give it a name, gamma. It's a matrix, ROT. Okay. So then, symbolically, right, delta prime equals to gamma ROT times delta. So that's the first important transformation that we've developed. Okay. Right. So this is what happens on the displacement side. What happens on the side of the forces? Okay. The relation between forces. Okay. So this is interesting. All right. Let me go back to node I, and the explanation here is going to be slightly different than that in the notes, but I like it better. Okay. And at node I, right, you have two pairs of quantities. So there is the delta 1 and F1, right? There is the delta 2, F2. There is the delta prime 1, F prime 1. And there is the delta prime 2, f prime 2, like this. Okay. So now let's think about work. Okay, what's work? If you recall from your earlier courses, it's some force times some distance. Okay? All right. So now let's write work, right, for node I. Okay, in xy coordinate system. Okay. Well, what you're going to find, right, is it's W, right, call it work, equals, right, force 1 that's developed in the node times displacement 1, right, that the node undergoes, right? But there's a second component of the force and the displacement that contributes to the work expression, F2 times delta 2. Okay? So basically, this is the work done by a force vector at node I, right, undergoing a displacement at node I. Okay? So one way to express this would be F1, F2, right? We package them into a vector, right? Row vector times a column vector that looks like delta 1 and delta 2. Okay? Now, there's another way to write the work. Okay? Supposedly now you're working in a local coordinate system. And the same quantity in a local coordinate system, right? So, let me see. So, work at node I in the xy coordinate system. Okay, it's the same amount of work, W, it's the same. Right? The amount of work that's performed should not depend on the coordinate system that you choose. If it does, then you're doing something wrong. Okay, right? Can be re-expressed as f prime 1 times delta prime 1 plus f prime 2, right, delta prime 2, which is the same as writing f prime 1, f prime 2 as a row vector times delta prime 1, delta prime 2 as a column vector. Okay, all right, so the two works are equal. Okay, what's next? Okay, now let's use the expression that relates local and global displacement. F prime 1, F prime 2, right, times, this is our rotation matrix, okay, cosine phi, sine phi, right, minus sine phi, cosine phi, this is our R, right, times delta 1 and delta 2. Okay? All right, so now let's compare this expression with this expression here. Okay? So delta 1, delta 2 part is the same between this one and this one. Okay? Which means that in order to obtain the same work, right, whatever is here must equal to the product of this quantity and that quantity. Okay? So another way to write this would be F, right, 1, F2, right, as a row vector equals to F prime 1, F prime 2 is a row vector times the rotation matrix. Okay? I can apply transpose to this relationship. okay? Basically, I take this, I put a transpose, I take that, I put a transpose, okay? And then I get F1, F2 as a column vector equals to what, right? If a transpose of a product, right, is you reverse the order of the product and transpose each item. R transpose times F1, F2 prime. Okay? So this is an important relationship. Right? So basically, so if your kinematics between the global and local coordinate systems are related through R, right? In order to match the work that's done by the forces between the global and the local coordinate system are related through R transpose. Okay? This is an important observation. And so then you can also write by the same analysis that F3 and F4 equal to, right, R transpose F prime 3, F prime 4, okay, by the same analysis. Which means that you can package everything into a one big matrix vector system, right, where you write F1, F2, F3, and F4 must equal to, right, F prime 1, F prime 2, F prime 3, and F prime 4, like this, okay? Right? The 1, 2, and 1, 2 are related through the transpose of the rotation matrix that becomes cosine phi minus sine phi, sine phi, cosine phi, 0, 0, 0, 0, right? 0, 0, 0, 0, cosine phi minus sine phi, sine phi, cosine phi, okay? And so what you see here, right, is that this is F, okay? This becomes F prime, right? And the two are related by gamma ROT transpose, okay? And so this is the relationship between two force vectors in the local and global coordinate systems. Okay, let me stop here, and then we'll continue in the next lecture, where we connect local, global, and basic systems. And what's going to happen is you're going to see an object that pops out, which is a stiffness matrix for the bar truss element, completely written in terms of the global coordinate system quantities. Okay? And that's what you want for your analysis.